Okay, so today we will be looking at the duality theory. We have already seen it in the previous lecture. We'll just go over duality theory, and I'll give you a graphical illustration of how it works. And then we'll look at optimality conditions. So this is what we had looked at previously, primal and dual forms. And then I'll give you the graphical illustration. And then I'll introduce some definitions pertaining to optimality, and then necessary and sufficient conditions for optimality. And the fifth bullet would have been a graphical illustration of these optimality conditions, but that we'll do in the next lecture, along with some examples. Anyway, so primal and dual forms, we'll do a review. This is a constraint optimization problem. These are the inequality constraints, and these are the equality constraints in scalar form. And this is the objective function, f of x, which is a mapping from n dimensions, which is the domain of x, into scalar. And in vector form, we can write it in this manner. G and H here are vector functions. And this is the feasible set. F is the set of all x's which satisfy the constraints. Both the inequality and the equality constraints are satisfied. Now, suppose you are given an optimization problem where you have to maximize a certain function with these constraints. All you have to do is replace f of x with negative f of x, and then you will be doing the minimization. If you have a greater than equal to constraint, then all you have to do is replace g of x with negative g of x, and then it becomes a negative g of x is less than equal to constraint. So this is the objective function, and the constraints. The Lagrangian we've seen is equal to this. Lx lambda mu equals the objective function plus summation lambda I gi of x. Lambdas are the dual variables for the inequality constraints, and then plus summation mu j hj. And these mu j's are also dual variables, but they are associated with the equality constraints. Now, these mu's are unrestricted, but these lambdas must be greater than equal to 0. And therefore, lambda I gi of x would be of opposite signs. Remember that. Okay, and vectorially, this is what we have. And the Lagrangian would then be expressed in this manner. Fx plus lambda transpose g of x plus mu transpose h of x. And lambda, the vector lambda is greater than equal to 0. It means element-wise, each element of lambda is greater than equal to 0. And let's highlight this. This is the COP, standard form, which we shall use everywhere. And this is the Lagrangian. Now, we've looked at the primal function, theta p of x. So this is everything we saw. And now the primal function is this. Theta p of x is the supremum of the Lagrangian with respect to the dual variables. Lambda greater than equal to 0 and mu. So we are minimizing with the objective function with respect to x. So we are doing minimization with respect to x is the primal variable. So what we do is, in the primal function, we maximize over the dual variable, both dual variables, lambda and mu. And since we have done the maximization over lambda and mu, we are left with only the argument x. So theta p of x is equal to this supremum of the Lagrangian with respect to lambda and mu. Similarly, the dual, what we do is, now instead of maximizing with respect to the primal, what we are doing is we are minimizing with respect to, I misspoke. We are minimizing with respect to x. So here we take the minimum with respect to x of the Lagrangian. And since we have minimized over x, we're left with lambda and mu as the argument. So that's theta d of lambda mu. This is the definition of the dual, and we just saw in the previous slide the definition of the primal function. Okay, now we've started some properties. So the dual function is concave. And so this is the property of concavity. And then we saw that the maximum of the dual is less than or equal to the minimum of the primal. So the dual is concave. So it's like an inverted cup shape, and the top of it is theta d star. And that will always remain lower than theta p star, which is the minimum of the primal. And how do we get this? This is a direct outcome of the Minimax theorem. So you take a function, first minimize, and then maximize. You will get something that's less than equal to what you would have gotten if you first maximized and then minimized. Okay? Then we saw that under certain conditions, strong duality holds. That is, theta d star equals theta p star. So strong duality holds if the objective function and all inequality constraint functions, g's, are convex, and all equality constraints are affine. So this is what I've written down mathematically. So f of x is convex, gi's are convex, and the equality constraint h of x is written in this manner: ax minus b equals 0. And Slater's conditions are satisfied. What is Slater conditions? Slater's conditions are this. So there exists some x naught such that gi of x naught is strictly less than 0. And hj of x is equal to 0. So it satisfies all the constraints. So x naught is a valid solution. It satisfies all the constraints, and the gi of x is being strictly satisfied. In other words, gi is each inequality constraint is inactive. Okay, I'll explain that later. But what it also means is that just ignore the equality constraints. Let's drop all the equality constraints. What it means is that the feasible region F has a point in its interior. Okay, because x naught strictly satisfies these inequality constraints. Any questions? Okay, so now let's move on to the graphical illustration of what we just saw. Okay, we will look at a very simple case. We will not have any equality constraints, just an objective function f of x, of course, and just a single inequality constraint. G of x is less than equal to 0. Just a single inequality constraint. Now, x is multidimensional. It's a vector. Okay, so this is the domain of x. It's in n dimensions. And this is the range or the image. Okay, I'll use the word range. So this, what happens is, any point you take here, it will map to some point in this range. Okay, let's say both f and g have upper and lower bounds as seen in this graph. Okay, so g and f have lower and upper bounds. They're both restricted either way, upper bound and lower bound. Okay, and so take any x. Okay, find f of x and g of x, and you get this corresponding point here. This is the image of x, fx, gx, and this point will always lie somewhere in this blue shaded region. Okay? Now, special cases would be, we're looking for the minimum, so it could be unbounded in this direction. It could go towards infinity or whatever, we don't care, but this is just an illustration. Now, this is the g-axis, this is the f-axis. I forgot to tell you one thing. This is the objective function, the y-axis. So we are trying to minimize the objective function f, right? So we want to go downwards. Okay, and this x-axis is g. The y-axis is the objective function. Okay, and since we have g of x is less than or equal to 0, the right half plane is infeasible. That's why g of x is greater than 0. Okay, so when we will be seeking the constrained optimum, we are restricted to this side only, the left half plane, including the y-axis, which is the f-axis. That corresponds to g equals 0. Okay, so suppose we have an x, we find out fx and gx, and so we get the corresponding point here, fx, gx. And we can always read off what's the value of fx and gx. So gx is equal to -1, f of x is equal to 2, correct? For this little example. This is f of x, and this is g of x. Some other point, x, we'll get f of x and g of x. That will give us another point in the this blue region, the range. Yeah?
Is it necessary that the fx and gx both are bounded regions?
It's not necessary. But at least f of x must be lower bounded because we are looking for a minimum. Right? So at least in the left half plane, it must be lower bounded. Otherwise, the minimum in the feasible region would be -infinity. Okay, that's the only thing that we need to pay attention to. Okay, so our first aim is to find theta p star. Remember that theta p star is equal to the objective function in the feasible region. And in the infeasible region, theta p is infinite. Right? In the feasible region, theta p of x equals f of x. In the infeasible region, it's infinite. We are trying to minimize theta p to get theta p star, correct? And so we can ignore the infeasible region. So we will focus on only this blue region here. So what's theta p star now? It will coincide with the minimum of the objective function too. What's the minimum of the objective function? Visually, you can see that it's here, right? At this point. So what we can do is, to obtain theta p star, we draw a horizontal line that's tangent to this in the feasible region. It doesn't matter what happens to this blue shaded region, the range in the infeasible region. Okay. In fact, it's going down a little here, but we are restricted to the feasible region. So this is the point where we get theta p star. All we have to do is look at the feasible region, draw a horizontal line that's tangent, and then this is the value of theta p star. Because f is equal to theta p, right, in the feasible region. So this is our theta p star.
P stands for primal function?
P is for the primal. Okay. Now let's look at how to find theta d star. D is for dual. Okay. So now when we did theta d star, if you go all the way back, let me remind you that if you look at the definition, theta d, we are doing the minimization here, right? But we are just ignoring the constraints. Okay, we are just considering all values of x in order to do this minimization, okay, of the Lagrangian. And somehow it turns out to be feasible if strong duality holds and all that. Anyway, so back to here. Okay, so theta p star we saw. Now let's look at theta d star. And now we'll focus on the entire blue region here, including the infeasible part. Why? Because by definition, all we have to do is take the infimum with respect to the Lagrangian. Okay, so now this is our goal now, to find theta d star. Okay, and point to remember, we look at the entire blue region, all points FG. Okay, now these straight lines are the equations of each of these straight lines is of the form f plus lambda g equals constant. Okay, they have the same slope. The slope is equal to minus lambda. Okay, so this is f plus lambda g equals some value of the constant. For some other value, this is f plus lambda g equals constant. This is f plus lambda g equals constant. For some other value, okay, and so these are all contours of f plus lambda g equals constant, where lambda is fixed. Lambda is fixed because they all have the same slope, right? And the slope determines lambda. In fact, all these straight lines have a slope of negative lambda. Okay, so each of these is straight lines is an f plus lambda g equals constant. Now, what we can do is how to find what the value of the constant is. Look at the y-intercept or the f-intercept, right? At this point here, what's the value of g? Actually, along this vertical line, the f-axis, what's the value of g? Everywhere it's 0, right? So set g equals 0 and read off the value of f. With g equals 0, whatever is the value of f, that will be the value of the constant, right? So here, what's the f-intercept? 7. This is 5, 6, 7. So the y-intercept, or the f-intercept in our case, gives us the value of the constant. And what's lambda? Negative lambda would give you the slope of the straight line. Okay. So this is f plus lambda g equals 2 because the y-intercept is 2 for this straight line. For this straight line here, f plus lambda g equals negative 1.5. Oh, no, here, negative 3, the y-intercept. And here it's negative 8, well, it's further down. Are we good so far? Okay. And this is for some other value of lambda. Again, lambda is constant. Here, lambda is fixed at negative 1. excuse me, lambda cannot be negative. Lambda equals 1, and the slope is -1, negative lambda. Okay, so what's the value of the constant here? So this is f plus lambda g equals y-intercept is 5. So f plus lambda g equals 5. This corresponds to, this dotted line here corresponds to f plus lambda g equals 1, and so forth. This is corresponding to lambda equals 0.5. The slope is negative lambda. Okay, and you can again read off the values of the constant from the y-axis. Now let's throw in this region here. That's the set of all f and g, the range of f and g. Okay, now we want to find fx plus lambda gx for any given x, and lambda equals, suppose x is fixed at some value and lambda is also fixed, and let the value of lambda be 0.5. What we can do is, one way to do it, excuse me, is to find fx and gx separately, right? And that would be this point here. We can read off, okay, so gx is -5, f of x is, whatever it is, 3.5, right? And since lambda is 0.5, you can evaluate f plus lambda g. But for our graphical reasoning that will follow, we will find f plus lambda g in another manner. Okay, in a more, instead of this straightforward manner, we'll look at it in some other way. So this is fx plus lambda g, fx comma lambda gx. This is the point. Okay, what we do is, we draw a straight line passing through that point, and the equation of the straight line being f plus lambda g equals constant. Lambda equals 0.5, so the slope of this straight line would be -0.5, negative lambda. Okay, and wherever this guy here, this straight line, intersects the f-axis, that's the f-intercept, that would give us the value of fx plus lambda gx. Are we clear about this? No questions? Okay. Now, this is an absolute no-no, because look at this straight line here. It has a positive slope of 0.5. So that means lambda equals -0.5. We cannot have negative lambdas. Okay, so we will not consider cases like this. Lambda must be greater than or equal to 0. Okay, now we looked at here, we fix x and lambda, right? And so we get a certain point, and then we, since lambda is constant, we draw the straight line with the corresponding slope of negative lambda, and we read off this value. Next, we consider when x is varying. Okay, so x is multidimensional. Let's say we have levers to control each axis of x. Okay, and so we are fiddling around with the axes. And as we do that, we will be migrating like this inside this blue region. Correct? Okay, first, suppose this is the trajectory that we take. Okay, now we're going to fix lambda at 0.5. X is varying because we are adjusting those levers to change x. So let's look at what happens to f plus lambda g. Our goal is to find theta d of lambda, which is minimum with respect to x of fx plus lambda gx. Okay, and lambda has a certain value. We are trying to evaluate lambda, theta d of lambda when lambda equals 0.5. Okay, so At this point, if this were f, x, and g of x, since lambda is fixed at 0.5, we draw a straight line with slope negative lambda, right? And this f-intercept, this point, would give us f plus lambda g. Okay, just f plus lambda g, not minimum with respect to x of f plus lambda g. It will just give us f plus lambda g. Then here, as we are adjusting our lever, we landed up here, and here again we draw this straight line with slope negative 0.5, and so f plus lambda g is this point here, correct? Wherever it intersects the f-axis, the y-axis, the vertical axis. Okay, and here, so what's happening to f plus lambda g? We are adjusting x. X is varying, okay? And what's happening to this f plus lambda g? It's going down, right? Correct? Here it's further down. This is f plus lambda g. We changed x again. This, again we changed x, and now this is our f plus lambda g. It's 1. F plus lambda g equals negative 0.3 or something. This is f plus lambda g, whatever this value is, 1.7 or something, negative 1.7. Okay. Now, if I further tweak x, what happens? It takes this trajectory. So what's the minimum of f plus lambda g when x, I was tweaking my x, playing around with x to see where I'll get the minimum, right? So this was the point where I got the minimum of f of x plus lambda g of x. So this is the minimum value of f plus lambda g. And that's, by definition, the minimum with respect to x of f plus lambda g gives you theta d, corresponding to lambda equals 0.5. Are we clear? Okay. So, how do we get theta d of lambda? Lambda is given. Okay, how do we obtain theta d of lambda? We draw a straight line with slope negative lambda that's tangent to this range, the blue region. Okay, and again, let me remind you, it could be on the other side too. Okay, because we are ignoring the feasibility conditions on the primal. We are just blindly minimizing the Lagrangian. Okay, so this is theta d lambda when lambda equals 0.5. Okay? Now, let's consider lambda equals 2. So, what I do is I again draw a straight line with slope negative 2, and that's tangential to this blue region, and then I read off the y-axis. That gives me theta d at lambda equals 2. Okay, so we have now found out a way to locate theta d of lambda for any lambda. How do we do that? By, since lambda is given, we draw the straight line that has a slope of negative lambda, and that's tangential to this the range of f and g, this blue region. This is theta d when lambda equals 1. The slope of this straight line is negative 1. This is theta d lambda when lambda is 0.5. So, as we vary lambda, what happens? Theta d lambda is changing. We had theta, for lambda equals 2, theta d lambda was somewhere here. Okay? For lambda equals 1, theta d was here. For lambda equals 0.5, this was theta d lambda. Okay. I don't know what this, I just ignored this, lambda equals 0.33. Okay. Now, this is corresponding to lambda equals 0.35. Note that this straight line with slope negative lambda is tangential at both these points. Okay. So, my claim is that this is theta d star. Okay. Look, it was lambda was always lower than this theta d star, right? Oh, sorry. This is my theta d star. And here the values of lambda are below that, right? So this is theta d star. Okay. What is theta d star? The maximum value of theta d lambda. Okay, why is that? Because the slope is 0.35. Here I was considering slopes that were more than 0.35. Okay, now suppose I keep reducing lambda further, below 0.35. Okay, this is for lambda equals 0.15. Now the tangent, point of tangency is here. It changed from somewhere here to here. This is the lowest value of lambda. Okay. Lambda can never be negative, so this is lambda equals 0 is the lowest we can ever be. And so that corresponds to a horizontal line, and that's tangent at this point here. So this is theta d when lambda equals 0. Are we good so far? Sure?
So we need to take a tangent at the maximum value of the lambda.
No, from below, we just take a tangent, wherever it's tangent, and we read off the y-axis. Okay. That gives us the theta d lambda. Okay, each of these theta d lambda we obtain that way. From below, we got the point of tangency. The slope of the line is fixed, because lambda is fixed. Okay, and then wherever it's tangent, we read off the f-intercept, the vertical intercept. That gives us theta d lambda. Okay, and so we carry out this experiment. I'll show you graphically a little more. So this, I claim, is theta d star, the maximum possible value of theta d lambda. Okay, now let's delve further into why. So now I reduce lambda even further. So now you see that it's theta d lambda is going back downwards, right? Now this is for theta d lambda equals 0. So here it's the horizontal line. That's tangent. Okay, for lambda equals 0. Now, when we did the primal, if you remember, we did a horizontal line, but then we ignored the right infeasible region. It was only for the left side of this, whatever was on the left of this vertical axis. Right? That's how we determined the theta p star. Okay, so this is my theta d star here. Okay, so this is my theta d star. This is the highest possible value of maximum with respect to lambda of theta d lambda. Are you guys okay with this? Sure? Okay, now before we move on to duality gap, one little thing, concavity of theta d lambda. If you might have observed, as we were reducing lambda, it first went up and then went down. So let's start the opposite way. We'll start with the lowest possible value of lambda, which is lambda equals 0. So this is for lambda equals 0. It's a horizontal line, and so I put it here, okay? And then we'll gradually increase lambda. Lambda equals 0.15. Okay, I put this marker, I repeat it here. So it went up, right? I increased lambda a little bit, and theta d lambda went up, increased. Increase it even further, now it's 0.35. And this is the vertical intercept, and this is theta d of 0.35. This is where it was tangent at both these points. There were 2 points of tangency here at 0.35. Now, so this was the pivot so far, right? Somewhere here. Now the pivot changes to this part, somewhere here, right? So it will pivot around, this straight line will pivot around this point. Okay, so this is for 0.5. It went down even further. It went down, actually it didn't go down further. It now started going downwards after this red point. This is for lambda equals 1. I keep increasing lambda each time. For lambda equals 1, it went down here. Lambda equals 1.5, it's here. Lambda equals 2, it's here. Okay, so you see that this is a concave function, an inverted cup shape. Okay, and that illustrates graphically that theta d lambda is the dual function, is, at least with respect to the lambdas, it is concave. Okay, now let's look at the duality gap. So this is theta p star. For theta p star, what did we do? We ignored the infeasible region where g was greater than 0. And on this side, we drew a horizontal line that was tangent. And that gave us theta p star. And then for theta d star, what did we do? We found a point that was tangent at both these points. And that gave us theta d star. And visually, you can always see why theta p star will always be greater than equal to theta d star. Okay. So this is the duality gap, which is theta p star minus theta d star. Are we good? This is where strong duality holds. Theta p star equals theta d star. I never said that it satisfies Slater's conditions or something. Remember what's Slater's condition? There must be a point which is strictly feasible. So G must be strictly less than 0, right? Okay.
I have a question that we are actually making a plot between f of x and g of x.
Correct.
So these x are actually the variables that we need to find the optimal point. Like we change the values of
Yeah, x and lambda.
Yeah.
Correct.
So this optimization point theta, shouldn't it be x rather than theta? Like what's the difference between x and theta?
X and theta or f and theta?
X and theta, because
X is in the domain,
yeah.
right? We are looking at the projection of all the x's onto the FG plane.
theta values? Like,
Yeah, so thetas are functions, right? Like Lagrangian. Okay, so this is, here you see that strong duality holds. Theta p star equals theta d star.
From this, we get x value by going back.
Yeah, exactly, yeah. That's hard to do. G inverse and F inverse or whatever. Okay.
We have the optimum value of the function f and g, and then we have to go back to the x.
Yes. To remind you, so once we locate the points, we locate a point somewhere here, right? And then we go backwards to here.
And the second point is, this is a 2D graph between f and g.
I just considered scalar inequality constraints, no equality constraint.
Okay. But if we have more than one constraint, then it will be 2D, 3D, or 4D?
Yes. Well, it's hard to show, but we could have another G2 axis pointing away from the screen or towards me. And then this would be a three-dimensional blob, this blue region. And instead of lines, we would have planes. We would have two lambdas, right, in that case. So the plane would, so you'll have two different lambdas because you have to define this plane using two different slopes. Okay. Okay, so this, here we had, this was the duality gap. Okay, and it existed, theta p star minus theta d star. But here you see that this is some other f and g, and this is the projection of all the points onto the fg plane. And here, this is both theta d star and theta p star. Okay. What's the value of lambda here? For theta d star, okay, this is also the tangent for the primal. For the primal, we have to draw a tangent that's horizontal. But for the dual, we have to take the tangent, right? But the tangent cannot have a positive slope because that would correspond to lambda less than 0. So this is the limiting case where for theta d star, we have a horizontal line as the tangent. So lambda equals 0 here. Okay. That's a point to note. That's a subtle point to note, but keep that in mind. Even if the first time around you don't grasp it, keep this in mind. Okay. Lambda equals 0 here. And what's G? G is strictly feasible. G is strictly less than 0. Now this is where f is a convex function and g is a convex function, and so you'll get a shape like this. Okay, and this is, and strong duality will always hold. Okay, because Slater's condition is satisfied because you have at least one x naught which is strictly feasible. Okay, because you have this region, right? You take any point in this second quadrant, well, actually on the left half plane, you would always get a valid x, right? And at this here, theta p star equals theta d star. And again, g is strictly less than equal to 0, strictly less than 0, not equal to 0. Sorry, strictly less than 0 here. And lambda equals 0. This is another situation. Again, a convex function with a convex constraint. Now, for the primal, this is what you get, right? You're trying to minimize in the left half plane. You just ignore the infeasible region, the right side, right? And so for the primal, clearly you don't have to draw a tangent anymore. It's exactly this point, theta p star. But for the dual, you draw the tangent and it's again here. Now what's the value of lambda? This red dotted line seems to have a slope of around -1, correct? So lambda equals -1 in this case. And what can you say about G here at the saddle point? Since strong duality holds, you have a saddle point, right? So what can you say about G at that saddle point? G is equal to 0, not strictly less than 0. So it's the boundary of between the feasible and infeasible regions, right? It's on this axis, the vertical axis. So in these previous cases, G was strictly less than 0 at the saddle point, and lambda was equal to 0, even in this case here. No, not here, sorry. Okay, so lambda was less than, lambda was equal to 0 and G was less than 0. Okay, again here, lambda equals 0 and G is less than 0. Here, lambda is less than 0 and G is equal to 0. You see what's happening here. Okay, we'll visit this issue shortly. Okay, so this is another subtle point that you got from this graphical illustration. Here, Slater's condition is not satisfied. We don't have a, this is the projection of all f and g for all x's. Okay. At best, we get g equals 0. We do not get a strictly feasible valid solution where g is greater than 0. G is less than 0 on this side. G is less than 0. We don't have anything on this side, right? This blue region lies entirely on the right side where it just touches here. This is the optimal, I guess. Okay. But if I were to draw this blue region further right, then we wouldn't be able to get any x star. The constraint optimization problem wouldn't have any solution. Okay. And so this is Slater's condition for strong duality, right? This is the saddle point, and sufficient conditions for strong duality is f of x is convex, and we saw here these two cases here and here. F of x and g of x were convex. So here, f of x is convex, g, well, we had just one g we were considering, but gi of x is convex for each I, and hi of j of x, actually. My notation is, I usually write j of x is affine. And a strictly feasible solution exists, x naught. Okay. So this graphical illustration probably helped you understand duality. And if you remember, I told you that each equality constraint can be written as two inequality constraints. H of x equals 0 can be written as h of x is less than 0 and h of x is greater than 0. You have to satisfy both. Right? Okay. Okay, so now we move on to optimality conditions. And we already saw some things about, we got some insights about optimality conditions from that graphical illustration. Okay, so now moving on to the next topic, optimality conditions, and the graphical illustration of the optimality conditions we'll look at in the next lecture when we do some examples. So this is the objective function. These are the constraints. This is the scalar form of the constraint optimization problem. This is the vector form of the same COP, and this is the feasible region. All the constraints are satisfied. Okay, active and inactive constraints. Now, this is an inequality constraint. And we saw that it can be either strictly less than 0 or it can be equal to 0. Okay. And when it's strictly less than 0, it's, in other words, the saddle point, or the point X is in the interior of the feasible region. Ignore the equality constraints for the time being. Okay. Here, it's at the borderline between when gi of x is equal to 0, we are operating at the borderline between the interface between the feasible and infeasible regions, right? And that's when the constraint, we say that the corresponding inequality constraint is active. Active meaning it's on the borderline, it's a borderline case. The boundary between feasible and infeasible. Okay, that's what we mean by active. Otherwise, it's inactive. That constraint is inactive. Now, equality constraints are always active. In one way, you can look at it as two inequality constraints. H of x is less than 0 and h of x is less than equal to 0 and greater than equal to 0, right? When h of x is equal to 0, that means both the corresponding inequality constraints are satisfied. Did you understand what I meant? Did you understand what I meant? Well, all I said was this hj of x equals 0, this constraint can be written as to inequality constraint. Hj is greater than equal to 0 and hj is less than equal to 0. Correct? And when I say hj equals 0, it means that the greater than equal to condition and the less than equal to condition both are borderline cases, right? Did you understand, or? Well, it's just a small point and not important. All we need to remember is equality constraints will always be treated as active constraints. Okay, and inequality constraints may be active, that is operating in the boundary, or they can be inactive. The active set is the set of all indexes of all inequality, active inequality constraints. Gi of x is strictly equal to 0. Not less than 0, exactly equal to 0.
Dealing some kind of exactly the axis only. The region is boundary on the axis only.
Yeah. Well, if you look at, where was it?
But in the inactive
Here. G of x was equal to 0. Yes. But here, g of x was actually less than 0. And lambda, what could you have said about the lambda here? The lambdas were 0, well, no, ignore this case. This is saddle, sorry, you don't have a saddle point here. The strong duality doesn't hold. Here, lambda equals 0. Here, lambda equals 0. Lambda and g, you see one of them equals 0, the other one is negative. Here, lambda is negative. Okay, sorry, lambda is positive. One of them is equal to 0. The other one is non-zero. Here, g is non-zero, lambda is 0. Here, g is, again, non-zero. This is g, right? Around 2 point something. And lambda is 0. G here is 0, but lambda is now non-zero. So they're opposites, okay? So this is the active set. All the active inequality constraints and the equality constraints. all those indices, this is the active set. Okay. A regular point. X is a regular point. There's a definition. If the gradients of the active inequality and the equality constraints are all linearly independent. Okay, that's a regular point. In other words, I take the gradients of all the active inequality constraints. So for each index I, which belongs to I intersection active. Okay, so these are the active inequality constraints, and these are all the equality constraints. The equality constraints are always active. Okay, so this is if each of these I've transposed, so each is a row. Each gradient is now a row of this matrix. Okay, and so if this matrix has full row rank, then X is a regular point. So this is the definition of a regular point. And we shall hereafter assume, unless I specifically say that it's not regular, we'll assume that the point we're dealing with is a regular point. It would be, what would it mean if it was linearly dependent, not linearly independent? It would mean that two of the gradients, maybe they're pointing in exactly the same direction. And that's rare. Okay, so unless I mention otherwise, we will be dealing with a regular point. Constrained minima. So this shaded region here is the set of all feasible points. And this point is X star, and I draw a ball with radius r around X star. So X star is a local minimum if take any point in the intersection between this ball and this feasible region. The ball and the feasible region, the intersection of that. Okay, for any point here, f of x star is always less than equal to f of x. Take any point x here, not here, because this is infeasible here. Okay, the intersection of these two. That's the definition of a local minima. And if we replace this less than equal to with a strictly less than, then X star is a strict local minimum.
So X star will be any point inside the ball?
No, X star is the center of this. The center of this ball is X star.
Okay, I got it.
And ignore the ball everywhere in the feasible region. If this holds, then it's a global minimum. Okay, so these are the constraint minima definitions. Now we will wind up with some conditions. Okay. Back to this is the constraint optimization problem, COP. This is the Lagrangian in vector form. Stationary point is x star, lambda star, mu star, and assume strong duality holds. Now, at this point, x star, lambda star, mu star, it must satisfy these two conditions, right? These constraints. So g of x star must be less than equal to 0. H of x star must be equal to 0. These two conditions are for this stationary point here, or saddle point, x star, lambda star, mu star. These are called the primal feasibility conditions. And lambda star must be greater than equal to 0. This is the dual feasibility condition. So these are the primal and dual feasibility conditions. Trivial. And now, complementary slackness condition. see, if you remember the graphically, we just noted, actually we noted that twice, that either lambda is 0 or g is equal to 0. Correct? One of them must be 0, and the other one is non-zero. They have opposite signs, lambda and g. Okay, so the complementary slackness condition says that lambda star transpose g of x star equals 0.
These are some famous conditions.
Yes, these are the Kkk conditions. We'll get into that. Now, remembering that they have to be of opposite signs. G has to be negative or equal to 0, and lambda has to be greater than or equal to 0. So this is actually summation lambda I star gi of x star equals 0. So each of these terms can be either 0 or negative, right? Because lambda and g are of opposite signs. So when I say lambda star transpose g of x star equals 0, I mean that each of these terms separately is equal to 0. That's the only way this can be satisfied. Okay. So for each I, lambda I star gi of x star will be equal to 0. Okay, and this is the complementary slackness condition, and you observed that for our graphical illustration also beforehand. Okay. Lastly, okay, so this is what I meant. Since there are opposite signs, gi and lambda I, so their product, lambda I star gi star, must be always less than or equal to 0. Okay, and so in this summation, each term must be separately be equal to 0 if this whole summation is equal to 0. Then we have the stationary condition. Stationary is an adjective. I don't know if this is an English word, stationarity, but I'll just use it as a noun. Okay. Stationarity is when the derivative of the Lagrangian is equal to 0. Which means that derivative of f del f of x plus lambda I, summation lambda I del gi of x plus summation mu j del hj of x is equal to 0. Okay, this is what we mean by stationarity, stationary condition. Now, it means vectorially, this is what it, when you differentiate this with respect to x, del of this will give you this. And del of this, mu transpose h, will give you del of h times mu transpose. Differentiate, the derivative of this term is this term. Okay, and so what we are doing is, so we are differentiating with respect to x. So treat lambda and mu as constants. So lambda transpose g of x. When we differentiate with respect to x, we get this here, and this lambda transpose now moves from the left side to the right side, and it becomes a lambda without the transpose. And the same thing with this term here. Derivative of this term is equal to this term. Okay, and remembering that g and h are both vector functions, so their derivatives are matrices, the Jacobian matrices. Okay, so now let's briefly divert our attention to see why this is happening. The derivative of something like this becomes this. So this is the Jacobian. We'll define the Jacobian. So this is a function, m-dimensional function. For each scalar f, this is the gradient. It's a vector. It's an n-dimensional vector because x is in n as in New York dimensions. Now, this is the Jacobian of this vector function, del f of x. So each column is a gradient of one of those scalar functions. And this is how we differentiate A transpose A is a constant, A transpose f of x. Okay, so these are x, A, and f of x are given to us. This is A transpose f of x. So the Jacobian is this. Each column is a gradient of one of the scalar functions. This is del of A transpose. I can write it in this way, which turns out to be the same as if you replace this del f of x with this matrix here, you'll get del f of x times A. Okay, so this is the gradient of each scalar objective. So this is how we got, when we differentiated the Lagrangian, this lambda transpose and mu transpose moved from the left side to the right side, and we didn't have to transpose them any longer.
It is similar to A transpose B is equal to B transpose A.
No, that's a scalar.
Okay.
That's the inner product,
Yeah,
two scalars.
yeah.
This is, here we're looking at a matrix.
Yeah.
So this. Okay, this is a scalar function, but we are trying to do the derivative. Well, this would be, what you said would be the same as writing this as G transpose lambda. This would be H transpose mu.
If we see the equation of derivative.
Yeah. This is analogous to this situation here.
Yes, this equation. This right one.
Yeah.
So, shouldn't this be a derivative of fx transpose A?
Yeah.
So,
This is the same thing as derivative of F transpose A.
my question is this f of x, this transpose T is missing in this equation.
This is a matrix.
But
And this is, look at the dimensions. What's this? So x is n dimensions,
yes.
right? And A and F are m dimensions. Okay, so this is A transpose Fx, which is the same thing as F transpose A. Okay, just to finish off, so this is n by m dimensions, this Jacobian here, n by m. Oh, sorry, this side. This is scale, A transpose F is scalar. This is n by m times, this is A is m by 1. So this will give us n as a New York by 1 vector, right?
On one side it's scalar and on the other side it's metric.
No, this whole thing, A transpose F of x is a scalar.
It's a scalar. And the other one is a metric.
The derivative of that, since the derivative involves x1, x2, x3 until xn as a New York, xn, right? So derivative of A transpose F of the scalar, A transpose F of x, would be a vector, right? And so we get this equation here. Okay? Did you understand completely? Both sides are now vectors because A transpose F of x is scalar, but the derivative is a vector. And this is a matrix times a vector. So, necessary and sufficient conditions, we'll wind up with this. First order KKT conditions. Okay. Primal feasibility, dual feasibility, complementary slackness conditions, and stationary conditions. The derivative of the Lagrangian must be equal to 0. So this is analogous to unconstrained optimization. The derivative of the function would be equal to 0. Now the derivative of the Lagrangian is equal to 0. Okay, but these are sufficient conditions. So these are necessary conditions. Just as in the unconstrained case. In the unconstrained case, primal dual feasibility and complementary slackness wouldn't exist.
Yes.
Right? And the first derivative is equal to 0 is a necessary condition for optimality, but it's not always the case. So, theorem, if x star is a regular point, then there exists a unique lambda star and mu star such that these first order KKT conditions are satisfied. Actually, these three together would be called zero order conditions because we don't take the derivative here. This is the, okay. So this is the set of first order KKT conditions which are necessary for optimality. And the second order sufficient conditions is just like the second derivative must be greater than 0 for minima, right? So here, by default, we're trying to minimize. So the second order KKT condition says that the second derivative of the Lagrangian must be positive definite. Okay.
This actually become a matrix and a both positive definite concept will apply here.
Yeah. First derivative of the Lagrangian is a vector. Second derivative is a matrix. It's the Jacobian, actually, of the Lagrangian. Okay. So, with this, we end today's lecture. But you got insights. And in the next lecture, we will solidify our insights about the first order KKT conditions. Okay. With graphical illustration, and then we'll look at some examples. I refrained from establishing the KKT conditions, theorems. That would have been another couple of lectures, of at least one lecture, but I didn't do that. We just, let's say this suffices. Okay, so unless you have any questions.
And even these Kkk conditions have been observed from the graph of f and g.
Only the complementary slackness condition was. Actually, mostly it's this one which we have to prove, but I'll stay away from that. Okay, this suffices, and we'll do some examples. Any other questions? Okay, so we can end today's lecture.